Welcome back everyone. In this lecture we will actually see some problems. So that will actually give you some grip on what we have done so far. So I will start with this very elementary problem about nilpotent Lie algebras. So here is the first problem. So let G be a finite dimensional nilpotent Lie algebra. Suppose I is an ideal inside G. So let us assume I is non-zero, ideal inside G. So then we have the center of G intersection I is non-zero. Okay. So this is a very non-trivial fact. So this actually directly follows from this Engel's theorem. So let us prove this. So what is the proof? So we can actually look at the action of G on I via this adjoint action, and then we have some information about that action. We will just use that information to conclude this. So note that G acts on I via adjoint action. So what is the meaning of that? So you can define this map sigma from G cross I to I, sending given by x comma y sends to bracket xy. Okay. Since I is an ideal, so this bracket xy will be element of I for all x in G and y in I. Okay. So this is going to define as linear homomorphism from G to GL of I. So this is actually Lie algebra homomorphism. So in particularly, if you look at the image of this phi of G inside GL of I, so this will consisting of all nilpotent transformations. Why? Because so G is given to be nilpotent. So that implies if I look at add x for any x in G, so that is actually going to define a nilpotent linear transformation from G to G. So because add x is nilpotent on G, so if you restrict add x to capital I, so that is also going to be nilpotent. So that implies add x restricted to I is also nilpotent transformation. So that means this phi of G, if you think about it, this consisting of all this add x restricted to I, where x is coming from G. Okay. So that means this set is actually as a subset of GL of I consisting of nilpotent transformations. So this is all nilpotent transformations. So then using our Engel's first version, so we can get a non-zero x in capital I such that x will be killed by this action of G. So G kills x. Okay. So that means what? That means phi of y will kill x for all y in G. So that will imply this bracket yx is 0 for all y in G. So that means this x is indeed in the center. So this x is inside the center of G intersection I. So since x is by choice non-zero, so that proves that the center of G intersection I is actually non-zero. So this completes the proof. Okay. So we already proved that for G nilpotent Lie algebra, the center of that nilpotent Lie algebra must be non-zero, but this exercise actually strengthens that fact. So it says that for any non-zero ideal, the center of G intersects that ideal non-trivially. So this is a much more stronger version of what we have seen already. So now we want to actually give some characterization of this nilpotent Lie algebras. Okay. So let us start with the nilpotent Lie algebra. Again all these Lie algebras are finite dimensional. So, if you start with, okay, now we will just start with the Lie algebra. So, if G is nilpotent, then we know that any subalgebra and any quotient of G must be nilpotent. Okay. So, if G is nilpotent, so then that implies any subalgebra and any quotient, okay, for K being ideal, they are all, both of them are nilpotent Lie algebras. Okay. So, now one can ask the converse. So, suppose if you know that there is an ideal, so such that G mod K is nilpotent. So, whether can we conclude like K nilpotent plus G mod K is nilpotent, from that can we conclude G is nilpotent. So, we have seen already some example, like you can take a 2-dimensional non-abelian Lie algebra, that itself is actually gives us counter example that the converse of this is not true. Okay. So, with some additional conditions, whether we can get G nilpotent. So, that is what we are going to see. Okay. So, this exercise answers that converse part with additional requirement. So, what it is? So, let us look at it. So, you start with the Lie algebra G and then take K is ideal inside G. Okay. So, such that this G mod K is nilpotent. So, that is actually given to us, and further what we assume, we also assume add x restricted to K is nilpotent for all x in G. Okay. So, add x restricted to K will map K to K because K is being ideal inside G. So, then what we want to claim with this hypothesis, we can say that G must be nilpotent. So, obviously, the converse is true. If you start with nilpotent Lie algebra, then any ideal K will be nilpotent. In particularly, like G mod K is also nilpotent. In particularly, if you look at this add x restricted to K, so that will be just add x defined on K. So, that will be nilpotent. So, this is in a way actually gives us characterization for nilpotent Lie algebras. But how one proves this? So, if you think about it, this just follows from again Engel's theorem. So, recall what is Engel's theorem. So, if you know that G is actually subalgebra of GLV and consisting of nilpotent transformations, okay, this is a finite dimensional vector space. Okay. So, V is finite dimensional vector space. So, then if you take G to inside GL of V such that all elements of G are nilpotent transformations, so then we proved that G must be nilpotent as an Lie algebra. Okay. So, now how do you use this theorem to prove that here G is nilpotent? So, recall if you have a map T which is defined from V to V, so if you have a map T from V to V, suppose you have a subspace W which is T invariant. So, then you restrict T to W, that defines a map from W to W, and T also induces a map from V modulo W to V modulo W. Okay. So, you have two maps associated with this T if you have this W being T invariant subspace. Okay. So, then for some reason if you know that these two maps are nilpotent transformations, then using that you can say that T is nilpotent. Okay. It is actually if and only if. So, I will leave it to you to think about it. Okay. T is nilpotent if and only if T restricted to W is also nilpotent and T bar is also nilpotent. So, now using this exercise, so this is an exercise from linear algebra, you can see that this add x restricted to k is given to be already nilpotent. Okay. Now, if you look at add x bar, which is a map from G mod k to G mod k. Okay. Since G mod k is nilpotent, this add x bar will actually coincide with this add x bar will coincide with add of x bar or x plus k. Okay. So, that implies that this add x bar is also nilpotent. So, that implies that this add x bar is also nilpotent because G modulo k is nilpotent. So, now this map and this map both are nilpotent. So, that implies add x defined from G to G is nilpotent. So, since it is nilpotent for all x in G, so now using again Engel's theorem, you conclude that this add G is nilpotent, but add G is isomorphic to G modulo the center of G. So, up to center of G it is nilpotent. So, that implies G is nilpotent. Okay. So, this implies add G is nilpotent and that implies that G is nilpotent. So, that we have already seen. Okay. So, this proves that this characterization of nilpotency. So, now we are going to see one important exercise about inner and outer automorphisms, inner and outer derivations. So, this is actually kind of very interesting exercise. So, later we will see that for semi-simple Lie algebras, so what we are going to prove now is not going to happen. Okay. So, let me first state the result, okay, then I will make a remark later. So, you start with again G being nilpotent Lie algebra. So, let G be a finite dimensional nilpotent Lie algebra. Then the claim is there exists some outer derivation of G. So, recall what is inner derivation. Okay. So, you have this add G. So, that is nothing but add x, x is coming from G. Okay. This is all called inner derivations, and we saw that these inner derivations they actually sit inside this what is called derivations of G. Okay. And this add G is indeed ideal inside these derivations of G, and what we want to call outer derivation is something that is not in add G. Okay. So, some z inside derivation of G is called outer if this z is not in this add G. Okay. So, that is the definition of our outer derivation. So, now what we want to claim, we will be able to produce one outer derivation of G if G is actually a finite dimensional nilpotent Lie algebra. So, this actually requires some steps. So, first step is we will actually find out ideal of codimension 1. So, there exists ideal inside G of codimension 1. So, that just follows from the fact that G is being solvable, because G nilpotent implies G is solvable. So, that means the derived algebra must be proper inside G. Okay. So, now if we take any subspace that is actually contains this derived algebra, and contained in G of codimension 1, so that must be an ideal, okay, of codimension 1, because any subspace that contains this derived algebra must be ideal. So, since this is already, one can choose it to be like codimension 1. So, you can see that this must be ideal of codimension 1. So, now what we do? So, you choose x inside G difference I. So, then you can see that G can be written as I direct sum C x. Okay. So, G has this very explicit explicit description. So, now note that if I actually look at this centralizer of this ideal I, okay. So, the centralizer of ideal I, so which is those elements y in G such that y commutes with all elements of I, okay. So, that is actually the centralizer of I inside G. So, this is a subalgebra that we have already seen. So, our claim is this must be non-zero. So, this is my step 2. Okay. So, why this is actually non-zero? If you think about it, we already proved that center of G intersection I is actually non-zero. So, then if you take any z from this center of G intersection I, then you can easily see that this z must be inside C G of I. Okay. So, that makes this C G of I non-zero. So, now what we do? We actually choose n, okay, choose n in n such that this C G of I, this is actually contained in G power n, but C G of I is not contained in G power n plus 1. Note that this G power n sequence, okay, this lower central series actually that converges to 0, okay, because G is being nilpotent. So, that implies at some point C G of I will be contained in G power n, but not in G power n plus 1. So, such a n exists, there is no issue with that. So, then what we want to do? So, our step 4, we take z naught which is inside this C G of I, but not in this G power n plus 1. Okay. Then using this z naught, I am going to define a map delta from G to G. So, how delta is defined? So, you take delta of I to be 0 and then delta of x to be this z naught, okay, and extend it linearly. So, note that G is nothing but I plus C x. So, that is what we already observed. So, one can define it on this I and then x, extend it linearly, there is no issue. Now, what we want to claim? We want to claim this delta must be a derivation, delta is a derivation. So, that is actually a very simple check. So, if I take elements from this Lie algebra G, so it looks like a plus some lambda x and then b plus lambda dash x, okay, for some a b in capital I and lambda dash in C. So, this is how any given elements will look like. So, then if you compute what is delta of this bracket a plus lambda x and then b plus lambda dash x. So, then you can see that, so this has to be equal to 0. Why? Because this bracket a plus lambda x and b plus lambda dash x all will lie inside your ideal I. So, this is 0. Okay. So, the bracket a lambda x, b lambda dash x. So, this is element of I. So, by definition you get 0. So, to prove it is a derivation, we need to check that this is also equal to delta of a plus lambda x bracket with b plus lambda x plus a plus lambda x bracket with b plus lambda dash delta of lambda dash x. So, this is what we need to check. So, let us compute this right hand side separately. So, if you compute the right hand side separately, then what you get? So, here you can see that delta of A is 0. So, you get lambda z naught, and then here you get b plus lambda dash x, and then plus here you get a plus lambda x, and this lambda delta of b is 0. So, delta of x is z naught. So, you get lambda dash z naught. Okay. So, recall delta of x is z naught and delta of I is 0. So, that is how delta is defined. So, that forces that this is equal to, note that where this is z naught is coming from. This z naught is coming from the centralizer of I. So, in particularly z naught bracket b will be 0. So, then it will give me lambda dash bracket z naught comma x. Okay. And similarly, if you think about it, again z naught will commute with a. So, you get this side again lambda dash bracket x z naught. But note that this is z naught x, this is x z naught. So, it will be just using the skew symmetric, you can see that this is 0. Okay. So, that proves that delta is indeed a derivation. So, now what we need to check? We need to check delta is not coming from your inner derivation. So, on the contrary, assume that delta is actually coming from, let us say, add g. Okay. So, then what happens? So, delta will be add z prime for some z prime in g. Okay. Now, note that this z naught is nothing but delta of x. So, that gives us this is exactly equal to z dash comma x. Okay. So, now what do we know about this z naught? So, this z naught is not coming from g n plus 1, and this z naught is actually coming from the centralizer of I. So, these are all the two data that defines z naught. So, in particularly if I take delta of A, which is 0 by definition, then you get this is z dash comma A. Okay. And this is true for all A in I. So, that makes this z dash is inside the centralizer of this I. But the centralizer of I, if you actually go back to the choice of this n, you can see that this centralizer of I is actually contained in g power n. Okay. So, that means this is inside g power n. So, this z dash is inside g power n. So, that forces that z dash x, which is z naught, is in g power n plus 1. Okay. But note that z naught is not in g power n plus 1. So, that leads to contradiction. Okay. So, that proves delta cannot be inner derivation. Okay. So, here is the remark which is actually will be proved later. Okay. In case if we deal with what is called semi-simple Lie algebra. So, if G is semi-simple Lie algebra, then one can prove that this add G is exactly equal to the derivation G. Okay. There are no outer derivations. So, only inner derivations are possible. Okay. So, this is actually a first thing that we will prove. And the second thing, if we actually think about it, which maybe I will prove it in the next class, this derivation G, this will actually contain all its okay. So, one can talk about what is called this Jordan-Chevalley decomposition, okay, which we will denote it by JC decomposition. So, for this actually you should refer to the lecture that is about Jordan-Chevalley decomposition. Okay. So, which is proved, you can actually refer to that lecture. So, what it says, if I start with a linear operator on V, so where V is finite dimensional, again you can work over complex number, no issue. Then this linear operator can be written as sum of two operators, one is nilpotent part, another one is the semi simple part, and all these n and s, they will have some important properties. For example, this n and s, they are unique. So, there exists unique nilpotent n and semi simple s, such that this happens, and n s commutes as well as n t commutes and s t commutes. Not only that, this n and s both are given by polynomials in T. So, there exists polynomial p x and q x inside C x, such that this p of capital T will be equal to n, and then q of capital T will be equal to s. Okay. So, this is what called Jordan-Chevalley decomposition. This is the additive version of that Jordan decomposition. So, what one can prove, okay, for the derivations of G, okay, if I take delta inside derivations of G, then we can write delta equal to delta S plus delta N, where delta S is the semi simple part and delta N is the nilpotent part. Okay. So, what one can prove, both delta S and delta N, again that will be inside your derivations of G. Okay. So, that means semi simple part of a derivation is again a derivation, nilpotent part of a derivation is again a derivation. So, that is what this fact says, and these two facts are very important facts which will be proved later. Okay. So, this I will prove it in next class, and then we will use this to prove this later. Okay. Okay, I will proceed with other problems. Now, I want to actually prove an identity which will be very much used later when we define what is called killing form. Okay, this identity is actually nothing to do with now killing form. We do not need to know what is killing form, but anyway, just to this is a fact about operators on some finite dimensional vector space. Okay. So, here is the fourth exercise. So, you start with three operators x, y, z inside your endomorphism of V. Again, assume that dimension V is finite. Okay. That underlying assumption is always there. So, then what we can prove, if you compute this trace of these products, okay, the product x y, the commutator and product with z, okay, that is equal to the trace of. So, you can actually shuffle them, trace x bracket y z, and then which is equal to trace of bracket y z x. Okay. So, these three things are same. So, how you prove this? This is just you use this fact that trace of A B is same as trace of B A. Okay. So, this is just uses the fact trace of any A B is same as trace of B A for all A B inside your endomorphism of V. Okay. Now, I will prove only the first part, maybe I will leave it to you to prove the second part. So, the first part, for example, translate as follows. If I take x y times z, the bracket x y times z, then you can see that this is x y z minus y x z. Okay. So, then if you are computing trace, then the trace of this is same as trace of this minus trace of this. Okay. Then if you think about it, so this is same as trace of x y z. So, I am not changing this, and then but I will just shuffle this. So, then you can group it like y x and z, then this becomes trace of z y x. Okay. So, now again you just shuffle them, trace of x y z minus, if you just keep z y one pair and then x as second pair, then this becomes trace of x z y. Okay. Now, you can see that I can take out trace because it is a linear map. So, then it gives us x times y z minus z y. So, which is exactly trace of x into bracket y z. So, this is the identity that we wanted. Okay. So, trace of bracket x y times z is same as trace of x into bracket y z. So, if you think about it, the second identity is actually comes from the first identity. Anyway, I will leave it to you to check. So, now I will actually kind of recall some important facts about nilpotent transformations, because we have already come across a lot about nilpotent transformations as well as semi-simple transformations. Semi-simple means diagonalizable. Okay. So, I will actually kind of list out various characterizations of nilpotent transformations. Again it is okay to work with complex numbers. Okay. Again these characterizations will actually differ if you actually work with some other field. For example, if you work with the real field, some of this characterization may not be true. I am just listing it for only complex numbers. So, what is this characterization? What are these? Let us see. So, again let T be a map from V to V. So, it is a linear transformation. Okay. So, now you assume that dimension of V is finite. Okay. Again this is only true for finite dimensional. So, what we want to say, the following are equivalent. So, I am not going to prove all of these equivalences. So, most of them actually you know already. So, I am just recalling all these facts. Okay. If you are not comfortable with some of the things, you should actually try to prove. So, all these facts just involves elementary linear algebra, nothing more. Maybe I will try to prove one or two equivalents which you haven't seen before. So, what I want to say? I want to say T is nilpotent so that is equivalent saying that here is the trace condition. The trace of T restricted to any invariant T invariant subspace, that must be 0, and this is true for all T invariant subspace W of V. So, this is the first trace condition. The third condition, the trace of again T restricted to W. Now, maybe I will use V lambda, maybe that is your familiar notation, V lambda. So, that is 0. Again this is true for all eigenspaces V lambda of capital V, okay, and true for any lambda in C. So, what is V lambda? V lambda, those vectors in V such that this T V acts as lambda V. Note that V lambda could be 0 and V lambda is non-zero if and only if lambda is an eigenvalue for this transformation T. Okay. The fourth condition, which again uses in terms of eigenvalues. So, 0 is the only eigenvalue. Of T. So, what does it mean? It means that 0 occurs as eigenvalue with dimension V number of multiplicities. So, again this can be rewritten in terms of the characteristic polynomial. If you take the characteristic polynomial of T, then that must be of the form x power dimension V. The sixth condition, this can be again told exactly using what is called the minimal polynomial. The minimal polynomial of T of x. So, that should be some x power r for some R. So, that R can be made into less than or equal to dimension V. Okay. So, here this is characteristic polynomial and this is minimal polynomial. Okay. So, we already have 6 different characterization. So, now if we use basis and then write T in terms of some basis, then we know that strictly upper triangular matrix with respect to some basis also is equivalent to nilpotent maps. Okay. There exists a basis of V such that this T with respect to B is actually strictly upper triangular. Okay, strictly upper triangular. So, now if we talk about in terms of this Jordan-Chevalley decomposition, then you can see that the semi-simple part of or the diagnosable part of T must be 0. Okay. So, here is again another characterization which is again in terms of the trace. Okay. So, T is being nilpotent is equivalent to. So, we know that if T is nilpotent then the trace of T must be 0. Since T is nilpotent then all the powers of T also must be nilpotent. So, that actually says trace of T power k is 0 for all k in n. And if you think about it, this trace of T power k is 0 for all k is actually equivalent to T being nilpotent. So, this is another criterion. So, I will end with this 10th criterion which actually says if you take determinant of identity plus some epsilon times this T power I, then if this is 1, okay, this is true for all epsilon positive, basically some small neighborhood is enough, but let us make it like positive, not a problem, and I is in n. If this is true for this particular data, so then you can claim that T is nilpotent. Okay. What you can prove indeed, if you think about it, this is a determinant of identity plus epsilon times T. So, this will be in polynomial in epsilon. So, where the initial terms will be just identity, okay, sorry, 1 plus trace of this T times epsilon plus etcetera. So, this is polynomial in epsilon. So, now if it is 1, you can see that if and only if this trace T must be 0. Okay. So, that makes trace T power I is 0 using the given condition. That is why we need this to be true for some particular like smaller positive neighborhood of epsilon, that is enough. Okay. But anyway, I have written it for any epsilon. But again there are again other conditions also makes T nilpotent. For example, if you have W which is a T invariant subspace such that this T restricted to W is actually nilpotent and T bar which is defined from V modulo W to V modulo W. So, where T bar of V plus W is mapped to T V. So, this is nilpotent. So, then that implies actually T nilpotent. For example, you can take this W to be just the kernel of T. Okay. So, that is good enough to prove the converse. So, there are various this characterizations for T being nilpotent. So, one should be very familiar with all these things because we will use this left and right in what is going to come. Okay. So, that is why I have stated this. Again similarly one can list various characterization of semi-simple linear transformations. Okay. For example, one of the necessary condition, one of the sufficient condition is that if t has minimal polynomial and that has all distinct roots. Okay. So, minimal polynomial of t is having distinct roots will imply t is actually semi-simple. Okay. So, there are again various characterizations for semi-simple. I will advise you to revise that. So, I will actually stop here, we are running out of the time. So, I will continue again this problem solving session with some other problems. Thank you.